In a 1733 paper of a French mathematician, Abraham de Moivre, the bell curve was first introduced to tackle a problem about gambling. Since then, the bell curve has been applied widely, from height to IQ score. In this video, I'm gonna walk you through both statistical and mathematical aspects of the bell curve, from the definition and characteristic to its function and application. But before we actually talk about normal distribution, we first need to understand the mean and standard deviation definition. The mean is a measure of center, and the standard deviation is a measure of spread. The mean is just another name for the arithmetic average, which can be calculated by the summation of all data values divided by the total number of data points. The deviation is calculated as the following formula, telling us how close the data values are to the mean. So, what is the normal distribution anyway? Well, it's a special form of density curve with a bell shape, describing the tendency for data to cluster around a center value, or in this case, the population mean. The normal distribution can be found in many day-to-day circumstances. For example, let's take a look at this graph of the National College Entrance Biology exam score throughout 3 years from 2018 to 2020. Although it's not perfectly normal, we can observe that the majority of people score near average. Here we have the normal probability density function for a continuous random variable with a population mean mu and a population standard deviation sigma. Let's examine the further characteristic of the bell curve with this function. Now we understand what a bell curve looks like. Next, we are going to examine the population mean and population standard deviation, two factors that determine the shape of the bell curve. Firstly, the population mean value determines the position of the normal distribution. If we increase the mean, the curve will move to the right and vice versa. This is because the data will always cluster around the mean when it is a normal distribution. Secondly, the population standard deviation characterizes the spread of the bell curve. The larger the population standard deviation, the more spread out the distribution would be. Since it's a density curve, the total area below it remains 100% throughout the changes, suggesting that changing the width will also affecting the height and vice versa. By examining its first derivative and second derivative, the bell curve has one local extrema at x equals mean and two inflection points at x equals mean plus or minus 1 standard deviation. The bell curve is symmetric around its mean. As it approaches infinity or negative infinity, the bell curve approaches zero. Therefore, it has one horizontal asymptote at y equals 0. To summarize the bell curve characteristic, the population means and standard deviations completely characterize the shape of the bell curve. The bell curve has one local extremum and two inflection points. The bell curve is symmetric about its mean. The bell curve has one horizontal asymptote. Let's do one practice question of a bell curve. We can calculate the probability density by evaluating the integral of the probability density function. For example, we have the bell curve demonstrating the blood pressure of healthy individuals between 14 and 70 years old. The mean and the standard deviation of this distribution are given on the graph. We can calculate the proportion of the population having stage 1 hypertension by evaluating the probability integral of the function from 140 to 160. As the result, about 3% of the population has stage 1 hypertension. Summing up what we can do with the probability density function. Firstly, we can calculate the probability or the proportion of the population if the population is normally distributed, and secondly, we know the population means and the population standard deviation by evaluating the integral. Here is how we can calculate the probability density. Step 1. We need to identify the population parameters, which are the mean and standard deviation. Secondly, We calculate the probability density by evaluating the integral.